Welcome back. If you've ever worked in an electronics lab, you've probably faced this exact situation. You hook up your super expensive signal generator to an equally expensive spectrum analyzer, but the numbers just don't add up. The power you receive isn't what you sent. So today, we're going to play detective and solve the all-too-common mystery of power loss in cables.
Okay, so let's start with a perfect world. Ideally, a signal's journey is a simple one. It leaves the source, travels down the cable from Z equals 0 to Z equals L, and arrives at the load, completely unchanged. What goes in is exactly what comes out. Easy enough, right?
But we don't live in a perfect world, do we? You set your source to output a specific power level, but the meter at the other end, it's reading something lower. So where did that power go? It's like it just vanished into thin air somewhere inside that cable.
To solve this mystery, we have to understand our victim, the signal itself. We need to look at the anatomy of the wave as it travels, because the clues to where that power went are hidden in the physics of its journey.
And the first major clue is something called the attenuation constant, which we represent with the Greek letter alpha. You see, every real-world cable is what we call lossy. It naturally causes the signal to lose strength. Alpha is the number that tells us exactly how fast the signal's amplitude decays as it travels, and it's measured in napiers per meter. You can kind of think of a napier as a cousin to the decibel, just based on the natural log.
And this slide illustrates it perfectly. See that dashed line? That's the exponential decay envelope, and it's dictated by alpha. As our wave travels from left to right, its peaks get smaller and smaller and smaller, getting squeezed down by that envelope. The farther it goes, the more power it loses.
Now, this is where things get really interesting. You might look at a cable spec sheet and see a loss value, something like 4.5 dB per 100 feet. But that number, well, it's based on one single, crucial, and often overlooked assumption. This right here is the core of the mystery. This is the disconnect that trips up so many people. You trust the datasheet, but your real-world measurements are telling a totally different story, and you're left wondering why. Well, it's because the conditions that spec was measured under might not be the same as the conditions in your lab.
And here it is. This is the golden rule. If you remember one thing today, burn this into your memory. Every single loss specification you will ever read from a manufacturer is calculated assuming one perfect condition, a perfectly matched system. Which, of course, begs the question, what in the world does perfectly matched mean?
Well, a matched line is basically an electrical engineer's dream scenario. It's a setup where the impedance of the device receiving the signal, we call that the load, is a perfect match for the characteristic impedance of the cable itself. For most of the equipment you'll use, that magic number is 50 ohms.
And here's why that's so important. In a matched system, there are absolutely no reflections, none. The signal becomes a one-way street, flowing smoothly from the source to the load without any energy bouncing back. No U-turns, no traffic jams. It's this clean, simple scenario that manufacturers use for their specs.
Okay, so we get the why behind the spec sheet now. So let's forge the how, the mathematical tool that connects that spec to the physical reality of the signal decay. This is our master key.
Take a look here. On the left, you've got the power going into the cable. On the right, the power coming out. The formulas look almost identical, don't they? But there's one critical difference on the right. That little term, e to the minus 2 alpha L. That is our attenuation doing its work over the full length L of the cable.
So, if we take the ratio of the input power to the output power, all those other terms just cancel each other out, leaving us with this beautifully simple exponential. This ratio, e to the 2 alpha L, is the true fundamental measure of power loss in a matched cable.
But in our world, we love to work in decibels. So we take that ratio, we apply the 10 log base 10 rule for power, do a little bit of math, and we arrive at our master key. The cable loss in dB is simply 8.686 times alpha times the length. With this formula, we can unlock any manufacturer's spec sheet.
All right, let's put our master key to the test. It's time for our first case file. We're going to take a real-world cable spec and use our new formula to decode its hidden physical properties.
So here's our clue. We have a standard RG58U coax cable. The manufacturer tells us that at 100 megahertz, it loses 4.5 decibels over a 100-foot length. Our mission, should we choose to accept it, is to work backward and find that fundamental attenuation constant, alpha.
So we just take our master key formula and rearrange it a bit to solve for alpha. Then it's just a matter of plugging in the numbers straight from the spec sheet, 4.5 dB for the loss and 100 feet for the length.
And there's our answer, 5.18 times 10 to the minus 3 napers per foot. Now, this isn't just a number. This is the physical truth of this cable. It tells us that for every single foot of this RG58U, the signal's amplitude decays by this exact amount.
Pretty cool. Excellent. Case 1 solved. Now for our second case file, where we apply everything we've learned to that original lab mystery, we're going to predict the exact power reading at the end of our cable.
Okay, here's the setup. A 50 ohm source, 150 feet of our RG58U cable, and a 50 ohm spectrum analyzer. The source is pumping out negative 30 dBm. Given everything we now know, what power should we expect to see at that analyzer?
Okay, step 1, and this is the most important part. We verify the match. Source is 50 ohms, cable is 50 ohms, analyzer is 50 ohms. We are perfectly matched, so the golden rule is satisfied. Next, we calculate the total loss for our 150-foot cable, which comes out to 6.75 dB. Finally, because we're working in the wonderful world of decibels, we simply subtract the loss from the source power.
And there it is. The final reading on our spectrum analyzer will be exactly negative 36.75 dBm. Mystery solved. The missing power wasn't magic. It was just predictable, physical attenuation eaten by the cable along its journey.
So here's the main takeaway. The next time you're in the lab stringing some cable together, just remember, that cable isn't just a perfect wire. It is an active component in your circuit, and it has a quantifiable appetite for your signal. So always, always account for that loss.
We've cracked the case for a perfect matched system, but what happens when the load isn't 50 ohms? What happens when reflections get involved and start bouncing around in the cable? Well, that's a whole other story and a much bigger mystery for us to solve next time.